When you see chemical reactions written out in textbooks, it gives you the idea that you always have the exact right amounts for all of the reactants to be consumed completely in the reaction. In real life, in the lab, this is not the case. Usually you wind up using all of one reactant, and then you have some of the other reactants left over. The reactant that is completely used up first is called the limiting reactant, or limiting reagent. We say all the other reactants are present in excess. Here's an example you might come across in your real life. You want to make some peanut butter and jelly sandwiches for you and your friends. To make a PB&J, you need 2 slices of bread, 2 tablespoons of peanut butter, and 1 tablespoon of jelly. If we were to write this like a chemical equation, it would look like this. 2 slices of bread plus 2 tablespoons of peanut butter plus 1 tablespoon of jelly yields 1 PB&J. But what if you have in your kitchen 10 slices of bread, 6 tablespoons of peanut butter, and 4 tablespoons of jelly? Which ingredient are you going to run out of first? In this case, you can eyeball it and quickly come to the conclusion that you'll run out of peanut butter first. You have enough bread for 5 sandwiches, enough peanut butter for 3 sandwiches, and enough jelly for 4 sandwiches. So in this scenario, peanut butter is the limiting reagent. You have excess bread and jelly. Now let's do an example chemistry problem using the same principles. We'll look at each reactant, assume that it's used up completely, and calculate the amount of one of the products. Whichever reactant gives you the smallest amount of product is the limiting reactant. Here's the combustion reaction of sucrose. C12H22O11 plus 12O2 yields 12CO2 plus 11H2O. Start with 50.0 grams of sucrose and 50.0 grams of oxygen. Which is the limiting reagent? Here's our strategy. First, we start with a balanced chemical equation. Next, we calculate the moles of product from each reactant. And finally, we see which is the smallest. Step 1. Start by confirming you have a balanced chemical equation. If it isn't balanced, you need to balance it before you can begin. There are the same number of carbons on each side, the same number of hydrogens, and the same number of oxygens. Okay, this equation is balanced. Step 2. Find the molar mass of the reactants. We'll use this to convert everything from grams to moles. That will let us use the balanced chemical equation to make conversion factors. The molar mass of sucrose is 12 times 12.01 plus 22 times 1.01 plus 11 times 16.00 equals 342.34 grams per mole. So 50.0 grams of sucrose times 1 mole per 342.34 grams equals 0.146 moles of sucrose. Now we'll do oxygen. The molar mass of oxygen is 2 times 16.00 equals 32.00 grams per mole. 50.0 grams of oxygen times 1 mole of oxygen per 32 grams of oxygen equals 1.56 moles of oxygen. Step 3. Find how much product you would get if all of a reactant is used up. Now that we have the reactants in moles, we can use the balanced chemical equation to find the moles of CO2 they would produce if they were completely used up. 0.146 moles of sucrose times 12 moles of CO2 for every 1 mole of sucrose equals 1.75 moles of CO2. In other words, if all the sucrose reacted, it would produce 1.75 moles of CO2. Now we do the same thing for oxygen. 1.56 moles of oxygen times 12 moles of CO2 for every 12 moles of O2 equals 1.56 moles of CO2. If all the oxygen reacted, it would produce 1.56 moles of CO2. The 50 grams of oxygen produced less CO2 than the 50 grams of sucrose, So oxygen is the limiting reagent. Next, let's find how many grams of CO2 will be made. Since oxygen is the limiting reagent, that will determine how much CO2 will be made. Once all the oxygen is used up, the reaction stops, even though there will be sucrose left over. We found in Part A that 1.56 moles of CO2 will be produced. We'll use the molar mass of CO2 to convert this to grams. Molar mass of CO2 is 12.01 plus 2 times 16.00 equals 44.01 grams per mole. 1.56 moles of CO2 times 44.01 grams of CO2 per mole of CO2 equals 68.66 grams of CO2. Next, we'll find how much is left over of the other reagent. We made 1.56 moles of CO2. How many moles of sucrose does that correspond to? We'll use the balanced chemical equation to figure this out. 1.56 moles of CO2 times 1 mole of sucrose per 12 moles of CO2 equals 0.13 moles of sucrose. 0.13 moles of sucrose times 342.34 grams of sucrose per 1 mole of sucrose equals 44.50 grams of sucrose. Careful, that's not the answer. That's how much we used, and the question was how much is left. To get that, subtract how much we used from the starting amount. 50.0 grams of sucrose minus 44.50 grams of sucrose equals 5.5 grams of sucrose left over. And finally, we'll find how much of the limiting reagent would you have to add to use up all the excess reagent. In the last question, we found there were 5.5 grams of sucrose left. How much oxygen does that correspond to? We'll convert to moles of sucrose and then use the balanced chemical equation to find out how much oxygen that means. 5.5 grams of sucrose times 1 mole of sucrose per 342.34 grams of sucrose equals 0.016 moles of sucrose. From the balanced chemical equation, we see that for every mole of sucrose, we need 12 moles of oxygen. So we have 0.016 moles of sucrose times 12 moles of oxygen per 1 mole of sucrose equals 0.193 moles of O2. Use the molar mass of O2 to find out how many grams that is. 0.193 moles of O2 times 32 grams of oxygen per 1 mole of oxygen equals 6.17 grams of O2. So it would take 6.17 grams of O2 to react with the excess sucrose. Here's an example of why the limiting reagent idea is so useful. Silver nitrate reacts with sodium chloride to produce silver chloride for photographic film. The silver nitrate is way more expensive than the sodium chloride, so this reaction is usually performed with an excess of NaCl. How many grams of AgNO3 are needed to produce 200 grams of AgCl? First, we check that the chemical equation is balanced. AgNO3 plus NaCl yields AgCl plus NaNO3. And this equation is already balanced. Next, we'll find the molar masses of AgCl and AgNO3. AgCl equals 107.87 plus 35.45 equals 143.32 grams per mole. AgNO3 equals 107.87 plus 14.01 plus 3 times 16.00 equals 169.88 grams per mole. 200.0 grams of AgCl. Use the molar mass to convert to moles. So we multiply by 1 mole over 143.32 grams equals 1.395 moles of AgCl. Using the balanced chemical equation, 1.395 moles of AgCl times 1 mole of AgNO3 per 1 mole of AgCl equals 1.395 moles of AgNO3. Now we'll convert back to grams. 1.395 moles of AgNO3 times 1.69.88 grams per 1 mole of AgNO3 equals 237.06 grams of AgNO3. In real life, we would measure out exactly 237.06 grams of AgNO3 and put NaCl in excess. We'll run out of AgNO3 and have NaCl left over. This way, we don't waste any of the more expensive reagent. We're always looking for more topics to cover at Socratica, so please let us know in the comments which videos you would really like to see next. If you found this video helpful, give it a like and share it with your friends. Don't forget to subscribe so you'll hear whenever we publish a new video. And finally, for the die-hard Socratica fans out there, we'd love for you to join our team on Patreon. You'll be helping us make more of these outstanding educational videos. Thank you.